I'm happy to be here. Thanks for sticking until the last talk of the session, and I'm here to present some of the work that we did at UCSD in continuation with what Ushashi and Professor Sakutai just presented. Basically, we have seen xRIG, and now I'm going to show how can we build new applications which are more driven for the physical layer, particularly MIMO applications. So, continuing, ORAN basically doesn't need much introduction here, but I want to give a flavor of how I understand and I build applications and what are the motivation for me. Just like how we know for any smartphone we have so many applications, right? And if we want to develop these applications, they need access to the fundamental resources or the hardware like cameras or microphone or touch, and it is the Android or iOS operating system that enables development of these applications. And this is where our focus is. We are building RAN intelligent controller that will provide access to the underlying RAN functionalities. Exactly what functionality that we will discuss, and that depends on different applications. But finally, it will enable app developers to build these applications, and we will show we have already seen a couple of these applications, and I'm going to show a new application that we have been building. In the context of ORAN, we have already seen that there are a lot of different intelligent controllers exist. We have the traditional ones, which are cRIG or dRIG, and the one which Ushashi just presented about xRIG, which provides more real-time control for PHY or MAC layer applications, which can control particularly DU and some RU functionality depending on the split. And finally, our goal is to build these new applications, and our focus would be on building micro apps which are built on xRIG platform for real-time control. So, looking into this applications that will enable flexible app development in RAN. So, looking into all the state-of-the-art controllers that are out there, and when we started this work, most of these controllers are either proprietary, which are not accessible to research community like us, and controllers that are built more real-time, more open source. They are mostly towards developing applications at higher layers. We have seen a lot of talk here as well for network slicing, resource allocation, and we just have seen scheduling. So, we went ahead with our xRIG platform, and we asked the question, can we extend it to build more physical layer applications, particularly for MIMO and millimeter wave. So, with that goal in mind, we took the xRIG controller. We know how it connects with ORAN on one side, and it provides a platform to build applications. We started looking into what we want to build this MIMO application, and what we want from the RAN is it should provide us a particular RAN configuration that supports MIMO. It should give us MIMO channel measurements, and it should give us performance metrics like SINR, blur throughput, which can evaluate whether our MIMO is working well or not. On the other side, our apps will help the Open RAN establish better beamforming or beam nulling solution. In case there is an interferer, we can do interferer aware beamforming. We can do new MIMO functionalities like user selection, antenna selection, even create new domains of work like localization, tracking, and simultaneous or joint communication and sensing. So, all these functionality are possible if we build our MIMO apps through this controller. So, we have built a version of controller in with srsRAN 4G that is already open source, and we have published it in a conference earlier this year. And what I'm going to show is a new version of our app, which now works with srsRAN 5G. So, again, to motivate for this development that we are doing, if we want to build any MIMO application directly into srsRAN, we have to look into hundreds of lines of code, particularly that are focused on file layer processing, and it's quite hard, right? With our app, basically it's a couple of lines of code in Python, which is very easy, and once you have access to how to get the channel, use the channel, build application, and it will be deployed in real time into the RAN. So, how we do that? We have this deployment with user connected to srsRAN with 4 antennas. It supports 4x4 MIMO. We collect this data in ORAN, and then we build our xRIG platform, particularly MIMO RIG, which supports MIMO applications, And to connect these two systems, we use the standard GMQ libraries, right? The key challenge is how exactly and where exactly to put these GMQ libraries into the srsRAN. So we have access to MIMO channel data on one hand to go from srsRAN to our controller, and on the other hand, when we create a new beamforming policy, this policy has to go back from our controller to the srsRAN. So I'll discuss in more detail about different parts and components that we have built or enabled to develop this platform. So first, let's look into how do we build this GMQ pub in srsRAN to open interface to stream MIMO channel to our application. So here we looked into uplink PUSCH channels. It has DMRS slot, which gives us UE sends specific pilots which are well known to the base station. It is uplink, right? And we estimate the channel from there. So we particularly look into a file, PUSCH processor implementation, which gives us access to these channel measurements. And as you can see, we have channel across 4 ports, across all subcarriers or resource elements per slot. So it's a 3-dimensional channel matrix. We aggregate this data across all 4 ports and all subcarriers into a package and send it this package via GMQ library to our application. And we run it in a conflict mode, where basically every slot this new channel is coming, and our application or the controller will collect this data from here. Now next we'll look into how we use this channel to build a new cool application. I will show one application in detail, which is jammer monitoring and anti-jamming. So here imagine you have a situation where user is sending uplink data. Base station, the normal uplink will work until you have a jammer or a device which is trying to block your signal communication. Now with our app, we call it Beam Armor app, and this app will make sure that it will create some kind of beamforming or beam nulling vector that will create a null towards the jamming direction, so that it maximizes the signal from the user and it creates a null or minimize the signal from the jammer. So the basic idea is simple. We know we can do some null steering to rotate the beam pattern, so that from the source of the jammer there is a null, so that the signal that we receive from the jammer is minimized, and so the impact of jammer would be minimum. So the key idea is to create this beamforming or beam nulling vector that can create a null towards the jammer direction. Okay. So to build this, one, we need channel. So this is the channel measurements that we did on the left without jammer and on the right with jammer. And as you can see, the channels are with 4 antennas. You can see from antenna 1, 2, 3, 4 there is, and then across all subcarriers we have around 612 subcarriers in this case. And you can see when we turn on the jammer, it affects all frequency subcarriers. And the main advantage of having this channel measurement across multiple subcarriers or resource element is that we can create nulling even in the presence of multi-paths, because each subcarrier is affected differently, and we have a nulling vector which is different for different subcarriers. And in that way we did experiment in a more realistic multipath environments, and this techniques work pretty well. So to show the pipeline of how exactly we create this Beam Armor app, we have this GMQ sub which collects the data first from the channel data in the package form from the srsRAN. Then we develop optimization method to calculate nulling matrix. Here the key question is, how do you know what is the jammer channel, how do you know what is the user channel? So when both jammer and user are on, what we receive is the sum of the channel from user and jammer. So we implemented regular or jammer monitoring, where we have basically real-time matrix, where when the jammer turns on, and before when the jammer was off, we have the clean user data. When the jammer is on, we have the data which has both jammer and the user, and we use some optimization to extract jammer channel, user channel separately, decouple them, and then create this beam nulling vector. So all this optimization we could do in our application with Python, and then send finally the beam nulling vector back to the srsRAN using our GMQ platform. Okay, so finally, what does srsRAN do once it receives this beam nulling vector we have to implement it in real time so that it can null the source of jammer in uplink. So we again have GMQ library which receives the beam nulling matrix. The beam nulling matrix is again across 4 antennas across 600 subcarriers, and it is received every time slot. It receives this and it looks into a particular file called equalize 1x(n). This is 1x4 receiver, and here you can see that it receives GMQ message, and then from there it receives an entire block across all ports and all subcarriers, and it breaks it down into per resource element and per antenna to apply into srsRAN. So all this code we will make open source, and if you want to work in this area, I'm very happy to discuss and collaborate in this area. So let's look into implementation and results. We have 2 implementation, one on BeamArmor 4G. The difference is in the 4G version also we have seen a part with Professor Sakutai's talk where it supports only 2 antennas. It allows raw IQ streaming, so there are no streaming for the channel, only raw IQ data, and there is no angle estimation. In the 5G version, we have 4x4 MIMO, 4 transmit antenna, 4 receive antenna, and here we can support PUSCH uplink channel across subcarriers, across ports, and we can also do angle estimation. So I'll show a demo of how we implemented this. So we have this setup where we did experiment in indoor and outdoor environment. Here we show in outdoor environment with the TX RX antenna, the PC. This is our jammer. We use a Pluto SDR with a power amplifier to generate a high power jamming signal. And user, we use a commercial smartphone. So here you will see our experiment where we collect channel data that I have shown across user with different angles. When the user is at 0 degree, we use that data to calibrate 4 antennas because there would be some frequency offset. And as you can see, we get very accurate angle estimation within 1 to 5 degrees of error. Now we turn on our jammer, we put the jammer up there, and then you can see that when the jammer is on, the signal strength goes up because there is more signal that we receive, but it results in low SNR and low throughput. So you can see the SINR is low, throughput is low, and bit error rate goes high. And in this way, we can detect that the jammer is there, and then we turn on our anti-jamming solution, and it will create a null towards the jammer. So these are the results. I mean, as you can see, the green line shows the original value without jammer, and then when we have BeamArmor off or BA off, then you can see because of jammer, the SINR goes down from 14 to around 2. But when we turn on our BeamArmor, we create a null, and we can recover back the original 14 dB of SNR. So it's extremely effective, works in real time, and it shows that by creating these nulls, we can create effective, we can recover the link under jammer. Other applications like localization, we have already seen these are some beamforming patterns that we get to estimate the user angle. And finally, I want to show one last plot where we show the impact of putting this GMQ libraries and streaming this channel data. It incurs a little bit of extra latency compared to the original srsRAN without having these extra functionality. And the extra latency is of the order of around 100 to 500 microsecond, which is much less than a TTI which we can handle. So thank you very much, and I'm happy to discuss, and if you have any questions, I'm happy to answer.